My name is Shaima. I'm a third-year PhD student. I work with Rob. And as you can see, my presentation is on minimizing energy consumption in cryogenic systems with attenuation for low error qubit operation. So first, we know that quantum computers are essentially composed of two things, the software and the hardware. So the software is responsible for the computations, the algorithms, and the information processing, while the hardware is the physical system that allows all these operations to be implemented, and this is where I mainly work. And the type of quantum computers we focus on require qubits to be operated at extremely low temperature. And then to control them or to apply quantum gates to them, we send microwave signals. But the problem here is that as microwave signals come from room temperature, so they carry heat with them, which can interrupt the qubits' operations and degrade their performance. So in order to protect the qubits, cryostats are used. And a cryostat essentially is a large refrigerator that goes to extremely low temperature, around 10 millikelvin. Okay. It doesn't work, okay. And this is where the qubit chips are mainly located, at this low temperature. And between that and between the microwave generator at room temperature, we have several cooling stages that progressively cool the microwave signals as they go down to the qubit. And you can see that the system has many other components, such as the wirings and other electronic elements. And here we focus on the attenuators. So now let's concentrate more on the attenuators. So as I said before, we have the qubits placed at the lowest temperature stage of the system. And then microwave signals are sent from room temperature and gradually cool as they pass through the different cooling stages, but they will still carry thermal noise that we don't want to reach to the qubits. So to get rid of the thermal noise or to reduce it, the experimentalists use attenuators. And the rule of the attenuators here is that they reduce the thermal noise by reducing the power of the microwave signal. So for example, if you have an attenuator of 20 decibel, only 1% of your power goes through and the rest 99% is dissipated as heat, which must be extracted by the cryogenic. So here I have an experimental setup where attenuators with specific dB values are placed at different cooling stages. And this helps protecting the qubits and so improving their quality, but it comes with an energetic cost because we'll need electricity to extract all the dissipated heat. So here we want to find a balance between that cost and between the qubits protection. So for this, the two questions that we ask are, what is the minimum electricity I can give to my system that maintains good qubits quality? And what are the required attenuators in the system to achieve this? So here we have the expressions for each of the error probability and the electrical power consumption for a system with k number of stages and k-1 attenuator. And both of these expressions were explained in Marco's paper that I showed there. And to briefly explain the idea behind them, I give this example of only two temperature stages. So you can see that we have the room temperature stage, and we have the qubit stage at temperature T1 with an attenuator A1. And then here we assume that the qubit is prepared initially in the state 0 and 1 equally. And because of thermal noise coming from room temperature, the qubits can be excited from 0 to 1 with the rate gamma times the number of photons arriving at the qubit, or it can relax with the rate in green. So the error basically comes from the contribution of these two processes. And the main part in it is the part highlighted in red, which represents, as I said, the thermal noise arriving at the qubit. And to determine it, we have to understand how the attenuator works. So we can see here that the attenuator reduces the thermal noise coming from the upper stage by the attenuation factor, but as the attenuator is at a certain temperature T1, it adds its own thermal noise. And N here is the Bose-Einstein function. So this is the basic mechanism behind this NQB, and so behind the final expression of the error probability. And here we assume doing a bit flip operation. So we know exactly the amount of power required by the qubit to do this operation. So we know exactly the output of the attenuator, and so we know the input to it, which is this power required by the qubit multiplied by the attenuation factor. So the heat here is equal to the input minus the output, and the amount of electricity that we need to extract this heat depends on the efficiency of the cryogenic system, because each cryogenic system has its own efficiency. So here, the electrical power consumption is equal to the heat needed to be extracted multiplied by the inverse of cooling efficiency at this temperature T1. So here, by generalizing for k number of stages, we get the general mathematical expression. So as I said before, we want to minimize the electricity that we give to the system, but at the same time, we want to maintain good qubits protection. So we want to minimize the first function under constraint of keeping the error probability small. And here we assume that we fix the number of stages, and also we fix the set of temperatures, and we fix all the other parameters. We only optimize over the attenuators that we assume n having one for each cooling stage. So to solve this problem, we use the Lagrange multiplier technique, which shows us that if you want to minimize a function f that depends on x and y, under constraint of another function g that depends on the same x and y, we construct a new function L that depends on the same x and y plus on the Lagrange multiplier parameter. And then we set the gradients to this new function to 0 to find solution which will minimize the function f. So for our case here, the f is the power consumption, and the g is the error probability that we want it to be equal to a certain required error. And the parameters that we optimize are the attenuations. So to carry out the optimization analytically, we defined an effective electrical power consumption, which is equal to the original one in units of p pi. And also we defined an effective error probability. And instead of optimizing over the individual attenuations, we optimize over the cumulative attenuation. And when we treat this with the Lagrange multiplier, the first thing we get is the Lagrange multiplier parameter lambda. And you can see that it depends on the constraint highlighted in green. And we get the optimal cumulative attenuations that depend on this Lagrange multiplier, and so on the constraints on the error probability. And finally, we get an analytical expression that minimizes the electrical power consumption at each required error probability for any system with any set of temperatures and with any number of stages, and also with any efficiency. Okay, so here we take this example of a 6-stages system with this specific set of temperatures, and here we assume constructing the efficiency at Carnot, extracting the heat at Carnot efficiency, sorry. And here in blue we have the power consumption versus the error probability when put in random attenuations in the system. And then when we plug our system into the expression that minimizes the electrical power consumption, we find this red curve. And you can see that no blue dot is below it. And also you can see that when the error probability is big, the electrical power consumption is small. But if you want to increase the quality of your qubit, you have to give your system more electricity. So here I have the attenuations that minimizes the electrical power consumption for each, as I said, given error probability. And when we plot this, we get a surprise, is that only the attenuation at the qubit stage varies with the error probability, while others, they remain constant. And we don't have a simple argument for that. We know that it's correct as we checked it multiple times by 3 analytical methods and 2 numerical methods. And as only A1 has a dependence on the error probability, you can see that it increases when the error probability decreases. So till now we made an assumption and we assume that nothing happened to the photons after arriving at the qubits and that they just disappear. But in fact, what happened is that they can either be absorbed and then dissipated at the qubit stage, or they can be reflected back to the microwave signal, which adds an extra parameter to the electrical power consumption. So we're looking at the new electrical power consumption. We can see that the minimum is when R equal to 1. And when we treat this with the Lagrange multiplier, we get the dashed line in black, which has a very complicated analytical expression that minimizes the electrical power, as we had to treat it with the perturbation theory. But as it is between the 2 solid lines of the simplified model and that have the simple analytical expression, and as these two are already close to each other, so we don't need to worry about the reflection. And we can now say that yes, we can use this assumption of the simplified model. And here we can see that the surprise that we had before in the simplified model, that only the A1 has the error probability dependence, is no longer true here in the more complete model. And that here we can see that all the attenuations from A2 to A5 varies with the error probability. And up to now, we assume that the qubit is sensitive to noise at only one frequency. So here we want to check if our method works when the qubit is sensitive to noise at multiple frequencies. So the simplest way to do this was by this multi-level system. And here, the error doesn't only come from the transitions in purple and in green from 0 to 1 and from 1 to 0, but also from transitions in red that takes the qubits out of its logical states. And here, we find that the error probability has the same structure as before, but the difference here is that instead of having gamma n of the 0 and 1 transitions, we have the gamma n of all the other transitions. So, so all the previous equations I showed previously are the same, except with this small replacement of the gamma n. So to conclude, I showed that the more attenuations we have, the more protection we have, but the more electricity we need to extract the heat. So here we gave an expression that minimizes the cost, but at the same time maintain good qubits protection. And also we checked when the model is more complete and when the reflection is included, and we found that the results are quite the same. And also we checked if the method works when the qubit is sensitive to noise at multiple frequencies, and the answer was yes. And thank you for your attention.
Thank you. Questions? There is a question there. You have a micro? Sorry.
Okay. Yeah. Thank you for the nice talk. I just have a small question about how you chose the range for the error on the qubits, because I saw on the plots that you're always in the order of magnitude of 10 to the power minus 6, right? Okay. Is there a reason for this, or?
Yeah, actually, we can do the optimization for any error probability we want. But if you look at this point here, you can see that the attenuation A1 here goes out of the logical region. So to continue the optimization, we have to fix that one to be 1, and then optimize over the other attenuations and redo the calculations for A equal to 1. So we can cover all
okay,
the
so it was a bit arbitrary. You chose that point to calibrate, and then you could do the rest.
No, it's not us that we choose, but the results of the optimization. So each time the attenuation goes out of the logical region, we fix it, and then we optimize over the upper attenuators.
How do you define this metric?
Yeah, which metric?
How do you define the error probability of a qubit? Usually you have gate errors, so it's error after, I don't know, which time?
Okay, so we assume doing one single qubit gate, and then we took the time step to be the slower gate, which is the 2 qubits gate, and then we included only the thermal noise inside the error probability.
So it's based on the gate error model.
Yeah.
So back to the question from Ariane, I've never seen such low error rates in any qubit modality. So why is this level? It's the level of errors you get with the electronics, the control. So
yeah, but as I said, but also the choice of the parameters we took, because we took a certain frequency and certain coupling and everything, so we can vary everything by.
So there are assumptions which motivate the
yeah.
numbers there. Okay, thanks.
And also here we consider the kernel efficiency, so everything changes when they.
Okay, one last question.
Thank you.
Yeah, sorry, I forgot. Yeah. So every time this A1 goes out of the logical region, we fix it, and then we continue the optimization and so on until we cover all the region of the error probability we want.
Last question.
Yes, hello. Yes, hi, thank you for the talk. I just wanted to ask, so I understand you consider one transmission line for each qubit of your computer. So have you ever thought, or are you planning to think also about multiplexing? So when you have one line delivering many signals for many qubits then.
Yeah. So for us here, we assume doing only one operation. So we have, as you said, one control line per qubit, but then we assumed having one operation, so the operations are not in a continuous way.
Okay, let's thank Mike again. And our last speaker,